Hello everyone. This video is Roll Center Part 7, and we're going to look at the lateral load distribution of a vehicle driving at a constant speed with a constant turning radius, and how this load distribution affects handling. In this video, we will learn about the types of lateral load transfer elements and make assumptions that can simplify the lateral load transfer system for the purpose of deriving the formula. Next, we will first explain the overall process of obtaining the lateral load transfer elements without using mathematical formulas. Next, we will explain various physical quantities and their symbols for deriving the mathematical formulas, and explain the calculation formula that can quantitatively derive the lateral load transfer. The main contents of the calculation formula are vehicle mass and lateral load transfer and roll center and roll axle, load transfer of unsprung mass, lateral load transfer of sprung mass, lateral load transfer distribution of sprung mass, and complete expression of all lateral load transfer elements. And finally, I will explain the lateral load transfer distribution moment factor and lateral load transfer gradient. In order to clearly explain the process of calculating the load transfer of sprung mass, I have repeatedly explained the same content in various ways. I have a quiz for you. Which of the following is related to the load transfer distribution that occurs between the front and rear wheels in a roll motion? Number 1, unsprung mass. Number 2, sprung mass. Number 3, lateral force acting on the roll center. Number 4, both unsprung mass and sprung mass. Please choose one of these. Let's learn about what types of elements in the lateral load transfer. There are 6 lateral load transfer elements that lateral acceleration generates. As explained in the previous videos, there are 2 types of vehicle mass, and both the sprung mass and the unsprung mass contribute to the lateral load transfer. As explained in the previous video E0075, if we introduce the concept of the roll center, the force generated by the lateral acceleration at the center of gravity of the sprung mass is divided into the force transmitted to the spring and anti-roll bar in the form of a moment, and the force that acts laterally to the roll center and is transmitted to the suspension link. The moment transmitted to the spring and anti-roll bar can be divided again into the front suspension moment generated by the sprung mass with respect to the roll center and the rear suspension moment generated by the sprung mass with respect to the roll center. Similarly, the force transmitted to the suspension link can be divided into the lateral force acting on the front suspension roll center by the front sprung mass and the lateral force acting on the rear suspension roll center by the rear sprung mass. Since the unsprung mass is not related to the roll center, no moment is generated about the roll center. The force generated by the unsprung mass can be divided into the lateral force acting on the unsprung center of gravity of the front suspension and the lateral force acting on the unsprung center of gravity of the rear suspension. The lateral load transfer for the lateral forces 3 and 4 of the sprung mass can be obtained by calculating the sprung weight supported by the front and rear suspensions, and then using the corresponding roll center height and the corresponding wheel track. The lateral load transfer for the lateral forces 5 and 6 of the unsprung mass can be easily obtained using the corresponding center of gravity height and the corresponding wheel track. The load transfer due to the lateral force generated by the sprung mass and the unsprung mass can be calculated independently from the front and rear suspensions. On the other hand, the lateral load transfer caused by the moment generated by the sprung mass on the front and rear suspensions is directly related to the suspension roll stiffness. The sprung mass is connected to both the front and rear suspensions, and rotates at the same roll angle along the longitudinal direction of the vehicle when lateral acceleration occurs. Accordingly, the magnitude of load transfer differs between the front and rear wheels depending on the ratio of the rear suspension roll stiffness to the front suspension roll stiffness. This phenomenon is called the load transfer distribution in the roll motion. In the lateral load transfer, the load transfer distribution between the front and rear axles is related only to the moment generated by the sprung mass. This fact is very important in the lateral load transfer. In order to derive the formula simply, the following 5 assumptions are made. First, the sprung mass is assumed to be rigid. Therefore, no torsion of the sprung body is assumed. Second, the roll angle of the sprung body is assumed to be small. Therefore, the cosine of the roll angle pi is 1, and the sine of the roll angle pi can be used as the roll angle pi in radians. Third, the roll axis tilt angle alpha is assumed to be small. Therefore, the cosine alpha of the roll axis tilt angle alpha become 1. Fourth, the longitudinal axis passing through the roll axis and the center of gravity is assumed to be in the same vertical plane that runs through the center of the vehicle. Finally, the tire deformation is ignored. However, here, if the suspension stiffness is too large compared to the tire stiffness, the suspension displacement becomes relatively small and the tire deformation becomes relatively large, so the tire deformation should not be ignored. In this case, the tire deformation should be considered. Let's review the roll center and the roll axis. The figure here is taken from the previous video E0069, vehicle roll center and the kinematic instant center. The roll center can be found at the front and rear suspensions, respectively. First, the roll center of the front suspension can be found on the lateral cross-section of the vehicle passing through the centers of the front left and right wheels. Similarly, the roll center of the rear suspension can be found on the lateral cross-section of the vehicle passing through the centers of the rear left and right wheels. Therefore, there are 2 roll centers, one for the front suspension and one for the rear suspension. If you connect these 2 with a straight line, you get a purple straight line in the forward and backward direction of the vehicle, as shown in the figure, which is called the roll axis. The roll center of the vehicle is the point where the vertical line from the center of gravity of the vehicle's sprung mass intersects the roll axis. When the vehicle turns, the lateral force of the vehicle acts outward from the center of gravity of the sprung mass. Here, the roll of the vehicle's sprung mass occurs around the roll axis. The roll angle phi that occurs at this time is assumed to be the same everywhere in the vehicle along the roll axis, because the object that makes up the sprung mass is assumed to be a rigid body. As previously explained, the load transfer of the sprung mass consists of 2 roll moments generated by the total sprung mass about each roll center of the front and rear suspension, and 2 lateral forces acting on each roll center by the each sprung mass of the front and rear, respectively. Let's find out how to calculate the load transfer of the unsprung mass. In the figure, MUF represents the front unsprung mass, MUR represents the rear unsprung mass, WUF represents the front unsprung weight, and WUR represents the rear unsprung weight. In addition, FUF represents the lateral force generated by the front unsprung mass due to lateral acceleration, FUR represents the lateral force generated by the rear unsprung mass due to lateral acceleration, HUF represents the height of the front unsprung center of gravity, and HUR represents the height of the rear unsprung center of gravity. The lateral load generated by the front unsprung mass FUF can be calculated by multiplying the front unsprung mass MUF by the lateral acceleration AY, since the lateral acceleration acts at the front unsprung center of gravity. If we multiply this force by the height HUF of the front unsprung center of gravity, we can obtain the moment generated about the point OF located on the road surface. According to the law of action and reaction, the moments must be in equilibrium about the point OF, so the moment obtained by multiplying the lateral load FUF by the height HUF of the front wheel unsprung center of gravity must be equal to the moment obtained by multiplying the front wheel track TF by the load transfer, and we can use this to obtain the load transfer. The same method can be used to obtain the load transfer generated by the rear unsprung mass for the rear. As explained, the load transfer of the unsprung mass is independent of the roll center and can be calculated using its own center of gravity. The derivation of these mathematical formulas will be explained in detail later. Let's continue by looking at the load transfer of the sprung mass. Let's look into the 4 types of lateral load transfers with respect to the sprung mass. Unlike the unsprung mass explained above, in order to calculate the load transfer of the sprung mass, you need to know the roll center and roll angle of the entire vehicle, the roll centers for the front suspension and the rear suspension, and the front sprung mass and rear sprung mass supported by the front suspension and the rear suspension, respectively. Both the left and right figures show the rear view when turning left. The left figure shows the front suspension, and the right figure shows the rear suspension. In the left figure, MSF represents the sprung mass acting on the front, and the blue cross mark represents the corresponding sprung center of gravity. When lateral acceleration is applied, a lateral force FSF is generated, and as a result, the sprung mass tilts by the roll angle pi, so the center of gravity of the sprung mass supported by the front wheel also moves to the right. Therefore, the point of application of the sprung weight WSF supported by the front wheel also moves to the right. As a result, the center of gravity deviates from the vertical line passing through the roll center. If the points of application of the front lateral force FSF and the front sprung weight WSF do not coincide with the roll center on the horizontal and vertical lines respectively, these forces generate moments about the roll center. The two forces FSF and WSF acting on the sprung weight center supported by the front wheel can be expressed as equivalent forces and moments about the roll center RCF as shown in the lower left figure. Here MSF is the sum of the moments generated about the roll center RCF by the force FSF and the weight WSF, and FSF is the lateral force acting horizontally on the roll center. If we analyze the forces and moments acting on the roll center, we can see that the moment capital MSF and the horizontal force FSF generate the lateral load transfer. Here, the moment capital MSF generates the force through the suspension spring and anti-roll bar, and front lateral force FSF acting on the roll center generates the force through the front suspension link. The rear suspension can be described in the same way as the front suspension. Since the lateral load transfer of the sprung mass is an important concept, let's take a closer look at the forces and moments acting on the roll centers. First, let's look at the moment acting on the roll center, and then the force acting on the roll center. The figure here shows the suspension of a vehicle turning left as seen from behind. The upper two figures show the front suspension, and the lower two figures show the rear suspension. The upper and lower two figures on the left show that the lateral acceleration acts on the front sprung mass MSF and the rear sprung mass MSR, generating forces FSF and FSR, and that the roll angle phi occurs, causing the center of the sprung mass to move laterally, so the points of application of the front sprung weight WSF and the rear sprung weight WSR change. As explained above, if the two forces on the left are equivalent to forces and moments about the roll center, they can be expressed as shown in the two figures on the right. As shown in the two figures on the right, since the roll angles phi are the same, the size of the front roll center moment MSF is determined by the size of the roll stiffness of the front suspension, and the size of the rear roll center moment MSR is determined by the size of the roll stiffness of the rear suspension. In order to calculate the load transfer generated by these front and rear moments, we need to know the roll stiffness of the front and rear suspensions, respectively, and the roll angle phi of the entire sprung mass. Next, let's find out the force acting on the roll center. In order to calculate the lateral force acting on the roll center, you need to know the sprung mass MSF acting on the front and the sprung mass MSR acting on the rear. You should clearly know that the center of gravity of the entire vehicle and the center of gravity of the sprung mass are different. In the figure on the left, the entire sprung mass is supported by the front and rear as a single rigid body. When calculating the moment acting on the roll centers of the front and rear suspensions, it is correct to treat the sprung mass as a single rigid body because the front and rear suspensions share one roll angle as the same value. However, since the lateral forces acting on the roll centers of the front and rear suspensions is calculated by multiplying the corresponding sprung mass supported by the front and rear suspensions by the lateral acceleration, the entire sprung mass must be divided into the sprung mass MSF supported by the front suspension and the sprung mass MSR supported by the rear suspension and used in each calculation. These two sprung masses can be calculated from the total weight received by the front suspension, the total weight received by the rear suspension, the unsprung weight of the front suspension, and the unsprung weight of the rear suspension. Here is a figure showing all the load transfer elements we have looked at so far. As explained above, the load transfer caused by the lateral force FUF generated by the front unsprung mass MUF and the lateral force FUR generated by the rear unsprung mass MUR can be calculated using their respective center of gravity heights and wheel tracks. However, the sprung mass tilts laterally with respect to the roll center RC. The sprung center of gravity moves outwardly when turning. Therefore, the load transfer caused by the sprung mass MS cannot be calculated simply by the sprung center of gravity height HCG. On top of that, the roll angle phi, the roll stiffness and roll center of each of the front and rear suspensions, and the sprung mass applied to each suspension should be known to calculate all four types of load transfer elements caused by the sprung mass. In order to calculate the load transfer of the front suspension roll moment MSF and rear suspension roll moment MSR, the roll angle and the roll stiffness of the front K phi F and K phi R rear must be known, and in order to calculate the load transfer of the front wheel lateral force FSF and the rear wheel lateral force FSR, the sprung mass applied to each axle and the roll center heights of the front and rear suspension must be known. The total sprung mass MS can be expressed as the sum of the front sprung mass MSF and the rear sprung mass MSR as shown in equation 1. In the physical quantities shown here, the lowercase m represents mass and the uppercase m represents moment. The roll moment MS generated by the total sprung mass of the vehicle about the roll center must be equal to the sum of the moment MSF generated by the front sprung mass and the moment MSR generated by the rear sprung mass, as shown in equation 2. The sprung mass connects the front and rear suspensions, and when a roll occurs while the vehicle is turning, the same roll angle occurs in the front and rear suspensions regardless of the suspension stiffness values of the front and rear. Knowing the roll angle of the sprung mass and the roll stiffness of each of the front and rear suspensions, you can obtain the front moment MSF and the rear moment MSR, respectively. The load transfer caused by the lateral force FSF generated by the front sprung mass and the lateral force FSR generated by the rear sprung mass can be calculated using the height of the roll center of each axle and the corresponding wheel track if the sprung mass, MSF and MSR corresponding to each axle are known. Now that we have looked at the overall concept of calculating the ideal load transfer distribution, let's look at how to derive the calculation formula. In order to express the formula for the distribution of lateral load transfer, let's first look at the vehicle dimensions and their symbols in the three-dimensional view of the roll axis. The four ovals represent the two front wheels and the two rear wheels. The total sprung mass can be expressed as the sum of the front sprung mass MSF and the rear sprung mass MSR as shown in equation 1. MS represents the total sprung mass. The yellow multiplication circle next to it represents the location of the total sprung mass center. MSF represents the front sprung mass. The yellow multiplication circle next to it represents the location of the front sprung mass center, and MSR represents the rear sprung mass, and the yellow multiplication circle next to it represents the location of the rear mass center. FS represents the lateral force generated by the total sprung mass. FSF represents the lateral force generated by the front sprung mass, and FSR represents the lateral force generated by the rear sprung mass. Therefore, the lateral force Fs generated by the total sprung mass Ms, as shown in equation 3, can be expressed as the sum of the lateral force FSF generated by the front sprung mass MSF and the lateral force FSR generated by the rear sprung mass MSR. HCG represents the height of the center of gravity for the total sprung mass. HCGF represents the height of the center of gravity for the front sprung mass, and HCGR represents the height of the center of gravity for the rear sprung mass. HRC represents the height of the roll center for the total sprung mass. HRCF represents the height of the roll center for the front sprung mass, and HRCR represents the height of the roll center for the rear sprung mass. In addition, h is the vertical height between the roll center and the center of gravity, which can be expressed as equation for using the roll center height and the sprung center of gravity height. When the height of the sprung center of gravity is greater than the roll center height, h is positive, as shown in equation 5. Conversely, when the height of the sprung center of gravity is less than the roll center height, h is negative, as shown in equation 6. For most vehicles, h is positive. Finally, angle alpha is the angle between the roll axis and the horizontal axis in the longitudinal section of the vehicle, and angle phi represents the roll angle of the sprung mass. Since the sprung mass is assumed to be rigid, there is no torsion, and therefore the front roll angle, the rear roll angle, and the total roll angle phi are all the same along the longitudinal axis for the entire sprung mass. Let's find out how to calculate the load transfer of the unsprung mass. Since the lateral force generated by the unsprung mass in the front suspension is generated by the lateral acceleration acting on the front unsprung center of gravity, the front lateral force FUF due to the unsprung mass can be obtained by multiplying the front unsprung mass MUF by the lateral acceleration AY, as shown in equation 7. Again, by multiplying this by the height HUF of the front unsprung center of gravity, the moment due to the front unsprung mass about the road contact point OF can be expressed as shown in the right side of equation 9. According to the law of action and reaction, the moment on the right side of equation 9 must be equal to the product of the front wheel track TF and the load transfer delta FZUF due to the unsprung mass, so using this, the load transfer equation for the unsprung mass in the front suspension can be expressed as shown in equation 9. Rearranging the equation 9 for the load transfer delta FZUF due to the front unsprung mass, we obtain equation 11. The load transfer due to the unsprung mass of the rear suspension can be obtained in the same way. Since the lateral force generated by the unsprung mass in the rear suspension is generated by the lateral acceleration acting on the rear unsprung center of gravity, the rear lateral force FUR due to the unsprung mass can be obtained as in equation 8 by multiplying the rear unsprung mass MUR by the lateral acceleration AY. Again, multiplying this by the height of the rear unsprung center of gravity HUR, the moment due to the rear unsprung mass about the road contact point OR can be expressed as the right side of equation 10. According to the law of action and reaction, the moment on the right side of equation 10 must be equal to the product of the rear wheel track TR and the load transfer delta FZUR due to the rear unsprung mass, so using this, the load transfer equation generated by the unsprung mass of the rear suspension can be expressed as equation 10. If equation 10 is rearranged in terms of the load transfer delta FZUR generated by the rear unsprung mass, equation 12 can be obtained. Let's continue to learn about the load transfer of the sprung mass. Before we derive the mathematical expression for the load transfer distribution, let me explain in more detail on the overall concept of how the lateral load transfer due to the sprung mass is calculated. The figure here is shown to explain the relationship between the lateral load transfer due to the sprung mass and the unsprung mass and the roll center. Here, the vehicle is turning left at a constant speed with a constant turning radius. The figure on the left is the rear view of the vehicle and the figure on the right is the side view of the vehicle. MS represents the sprung mass and MU represents the unsprung mass. When the vehicle turns, not all the mass of the vehicle moves relative to the roll center. The mass associated with the roll center is the sprung mass supported by the spring and anti-roll bar. The motion of the unsprung mass is the mass under the spring and is not related to the roll center. Therefore, the lateral load transfer of the unsprung mass is independent of the roll center and can be calculated based on its own center of gravity location. The The center of gravity of the unsprung mass is located on the vertical cross-section that includes the centers of the left and right wheels. The lateral load transfer of the unsprung mass is calculated independently for the front and rear suspensions. In contrast, the lateral load transfer of the sprung mass is calculated with respect to the roll center. In order to calculate the load transfer caused by the moment generated about the roll center, the roll stiffness of each of the front and rear suspensions and the roll angle of the total sprung mass must be known. In addition, in order to calculate the load transfer due to the lateral force acting on the roll centers of the front and rear suspensions, the roll center heights for the front and rear suspensions must be known, and also, the sprung mass supported by the front and rear suspensions must be known, respectively. The figure here is to explain the principle for calculating the lateral load distribution in the forward and backward directions caused by the moment due to the sprung mass. The black bar in the figure is supported by supports at both ends and can rotate without friction. As shown in the figure, a rigid rectangular body that cannot be deformed is attached to the rotatable bar. In addition, a spring is attached to each corner of the rigid rectangular body. The spring constants of the two springs in the front are the same, and the spring constants of the two springs in the back are also the same. As shown in equation 13, we assume that the front spring constant has a larger value than the rear spring constant. When no force is applied to the rigid rectangular body, it remains horizontal with respect to the ground, as shown in blue. When the force of the yellow arrow is applied to the rigid rectangular body as shown in the figure, the rigid body rotates, and at this time, the rotation angle is the same in the front and back. If the rotation angles in the front and back are the same, the amount of ground reaction force variation is naturally larger on the side with the larger spring constant. This is shown in the figure as sizes of green arrows. This same principle is applied to calculate the distribution of lateral load transfer at the front and rear wheels when a vehicle turns left at a constant speed with a constant turning radius. In the figure, the rectangular rigid body corresponds to the shape of the vehicle's sprung mass, and the moment generated by the force of the yellow arrow corresponds to the moment generated by the lateral force that the sprung mass receives during the turn. If the vehicle's sprung mass is considered a rigid body, the roll angle is the same for the front and rear wheels, so the lateral load transfer will be greater on the side with stronger suspension roll stiffness. Therefore, by adjusting the ratio of the roll stiffness of the front and rear suspensions, you can adjust the ratio of the load transfer between the front and rear wheels. Knowing the roll angle phi, front suspension roll stiffness, and rear suspension roll stiffness, we can know the load transfer between the front and rear wheels, and from these, we can also calculate the load transfer ratio. This time, let's look at the geometry of the center of gravity and the roll center for the sprung mass in the cross-section of the roll axis. The figure here shows the center of gravity and the roll center for the sprung mass along with the roll axis in the cross-section of a vehicle making a normal left turn at a constant speed on a road of a constant radius. The figure on the left shows the laterally vertical section including the roll center as seen from the rear, and the figure on the right shows the longitudinally vertical section including the roll axis. When the vehicle is not turning and is moving straight ahead at a constant speed, the distance from the roll center to the sprung center of gravity can be represented as h. The sprung center of gravity and the roll center are on a vertical line. When the vehicle makes a steady-state left turn with constant speed and constant road radius, the lateral force acts, so the sprung mass tilts to the right by phi. Therefore, the vertical distance from the roll center to the sprung center of gravity in the cross-section can be represented as h cosine phi, and the horizontal distance from the roll center to the sprung center of gravity can be represented as h sine phi. Let's calculate the moment generated by a vehicle turning left at a constant speed with a constant turning radius. When the vehicle turns, the sprung mass rotates by phi around the roll center, so the roll center and the sprung center of gravity are not on a vertical line, and therefore a moment is generated about the roll center RC. Additionally, the roll axis is tilted by an angle of alpha in the side view. From the figure on the left, if we find the moment about the roll center RC, we can obtain equation 14. In equation 14, ms is the sprung mass and ay is the lateral acceleration. Here, when the angle phi and alpha are small, the sine phi can be approximated as phi, the cosine phi can be approximated as 1, and the cosine alpha can be approximated as 1. This can be expressed as equation 15. If equation 15 is substituted into equation 14, we can obtain equation 16. In equation 16, Ws represents the sprung weight and g represents the gravitational acceleration. In the calculation formulas derived so far, the relationship between the roll center of the entire vehicle and the center of gravity of the sprung has been found, and the moment has been calculated from this. However, the calculation results from the overall perspective examined so far do not show how the lateral force of the vehicle is distributed to the front and rear wheels. Therefore, the calculation formula needs to be extended so that the influence on the front and rear wheels can be calculated, and for this purpose, the influence of the suspension stiffness of the front and rear must be included in the calculation formula. As discussed above, in order to obtain the load distribution due to the moment generated by the sprung mass, we need to know the roll angle. To calculate the roll angle, we need to find out the suspension stiffness of the front and rear wheels and the moment generated by the sprung mass in a vehicle driving at a constant speed with a constant turning radius. Considering both the angle alpha formed by the axis parallel to the ground and the roll axis on the longitudinal section of the vehicle and the roll angle phi of the sprung mass, we establish a moment equation, and then establish a calculation equation when these angles have small values, as in equations 15 and 17. The front suspension roll stiffness can be obtained as in equation 18, and the rear suspension roll stiffness can be obtained as in equation 19. When the vehicle turns, the moment generated by the sprung mass about the entire roll axis must be equal in magnitude and opposite in direction to the reaction moment generated by the suspension. The moment generated by the sprung mass about the entire roll axis can be obtained as in equation 14, as discussed above. The reaction moment occurring in the suspension can be expressed using the suspension roll stiffness and can be obtained as shown in equation 20. Since these two moments are equal in magnitude and opposite in direction, their sum must be 0. As explained, according to the law of action and reaction, the result of adding equations 14 and 20 should be 0, so equation 21 can be obtained. The roll stiffness K phi of the entire vehicle can be expressed as the sum of the front roll stiffness K phi F and the rear roll stiffness K phi R, as in equation 22. When the angle alpha representing the inclination of the roll axis and the roll angle phi of the sprung mass are sufficiently small, if equations 15 and 17 are substituted into equation 21, the cosine term of equation 21 becomes 1 and the sine term becomes phi, so equation 23 can be obtained. Equation 23, the moment about the roll axis, includes both the front roll stiffness and the rear roll stiffness. When equation 23 is rearranged in terms of the roll angle phi, the roll angle phi can be expressed in terms of the lateral force generated by the sprung mass, the weight, and the roll stiffness. Continuing, let's find the roll angle gradient for a vehicle driving at a constant speed on a road with a constant turning radius. If we rearrange equation 23 obtained previously for the roll angle phi, we can get equation 24. The expression for the roll angle phi obtained in equation 24 is used to calculate the load transfer distribution generated by the sprung mass for the front and rear wheels. By definition, the roll angle gradient is the value obtained by differentiating the roll angle with respect to the lateral acceleration, as shown in the second term of equation 25. Therefore, if we differentiate equation 24 with respect to the lateral acceleration ay, we can find the roll angle gradient as shown in the last term of equation 25. As shown in equation 25, the roll gradient is proportional to the sprung mass ms and the height from the roll center to the sprung center of gravity, and inversely proportional to the value obtained by subtracting the roll moment generated by the sprung mass from the sum of the front and rear roll stiffness. From the previously obtained equation 25, the moment arm h for the moment generated by the sprung mass due to the lateral acceleration can be obtained as a function of the roll gradient. In the figure, h represents the distance between the roll center and the sprung center of gravity. The distance h represents the length of the moment arm for the moment generated by the lateral force due to the sprung mass. If equation 25 is rearranged for the distance h between the roll center and the sprung center of gravity, equation 26 can be obtained. As shown in equation 26, the distance h from the roll center to the sprung center of gravity can be expressed as a function of the roll gradient r phi. Since the roll angle phi is obtained from the previously derived equation 24, let's derive an equation related to the load distribution of the sprung mass. The front suspension roll stiffness can be expressed as equation 18 by differentiating the front sprung moment MSF with respect to the roll angle phi. According to the law of action and reaction, the moment MSF generated by the front wheel sprung mass must be equal to the reaction moment of the vehicle, and the reaction moment of the vehicle can be obtained by multiplying the front load transfer delta Fz phi F by the front wheel track Tf. Therefore, equation 27 can be obtained. Similarly, the rear suspension roll stiffness can be expressed as equation 19 by differentiating the rear sprung moment MSF with respect to the roll angle phi. According to the law of action and reaction, the moment ms are generated by the rear sprung mass must be equal to the reaction moment of the vehicle, which can be obtained by multiplying the rear load transfer delta Fz phi r by the rear wheel track Tr. Therefore, equation 28 can be obtained. Equations 27 and 28 have the same roll angle phi, which can be calculated by equation 24. Since the front and rear wheel tracks are known, and the roll angle phi can also be calculated by equation 24, if the front suspension roll stiffness K phi F and the rear suspension roll stiffness K phi R are known, the front load transfer delta Fz phi F and the rear load transfer delta Fz phi R can be calculated. The front and rear suspension stiffnesses can be measured or calculated by computer simulation. Here is a graph of the front or rear suspension roll stiffness, taken from Dixon's book Tires, Suspension and Handling, page 237. The horizontal axis represents the roll angle, and the vertical axis represents the roll moment. Point A is the point where the roll angle is 0, and the slope at this point is defined as the suspension roll stiffness. Point B is the point where the roll angle continues to increase until it meets the bump stopper, and the suspension roll stiffness begins to increase further. Point C is the point where the roll angle continues to increase until it meets the droop limiter, and the suspension roll stiffness begins to increase again. Point D is the point where the roll angle continues to increase until the inside wheel of the turn leaves the ground, and the suspension roll stiffness begins to decrease. Having a front suspension roll stiffness graph and a rear suspension roll stiffness graph shown here, we can calculate the corresponding suspension roll stiffness for any roll angle, since we know the roll moment at any roll angle. From equations 27 and 28, since we know the wheel track and suspension roll stiffness for the front and rear, and have calculated the roll angle, we can calculate the front and rear load transfer amounts delta Fz phi F and delta Fz phi R, and from these, we can calculate the load transfer distribution ratio occurring at the front and rear wheels. Now that we have calculated all the factors needed to calculate the load transfer distribution of the sprung mass, let's derive the equation. We have previously derived the equation for the roll angle phi as in equation 24. Also, using the law of action and reaction, we derived the load transfer equation for the front wheel as in equation 27. Substituting the roll angle phi of equation 24 into equation 27 and arranging equation 27 in terms of the front suspension load transfer delta Fz phi F, we obtain equation 29. Similarly, substituting the roll angle phi of equation 24 into equation 28 and arranging equation 28 in terms of the rear suspension load transfer delta Fz phi R, we obtain equation 30. We can see that both front suspension load transfer equations 29 and rear suspension load transfer equation 30 include the same roll angle phi. In the next step, we will calculate the lateral load transfer due to lateral force at the front and rear roll center. In order to calculate the lateral force FSF acting laterally at the front suspension roll center, due to the lateral acceleration of the front suspension supported sprung mass MSF, and the lateral force FSR acting laterally at the rear suspension roll center, due to the lateral acceleration of the rear suspension supported sprung mass MSR, the front suspension supported sprung mass MS and the rear suspension supported sprung mass MSR must be obtained. The first way to find these masses is to find the longitudinal location for the center of gravity of the sprung mass, and then find the front and rear sprung masses. The second way is to subtract the front and rear unsprung masses from the total mass of the front and rear, respectively. I will explain the first method first. It must be clearly understood that the center of gravity of the total vehicle mass M and the center of gravity of the sprung mass MS are different. LSF and LSR are the lengths from the center of sprung mass to the front axle and rear axle, respectively, and LF and LR are the lengths from the center of mass of the total vehicle to the front axle and rear axle, respectively. The longitudinal center of gravity location of the sprung mass can be derived from the entire vehicle mass and the center of gravity location, the weight of the sprung mass, and the front and rear unsprung masses. The moment generated by the entire vehicle weight with respect to the rear wheel contact point must be equal to the sum of the moments generated by the front suspension unsprung weight and the front suspension sprung weight, and the relationship for these moments can be expressed as equation 31. By the same principle, the relationship for the moment generated with respect to the front wheel contact point can be expressed as equation 35. If both sides of these two equations are divided by the gravitational acceleration g, equations 32 and 36 can be obtained, respectively. Continuing, if equation 32 is rearranged for LSR, equation 33 can be obtained, and if equation 36 is rearranged for LSF, equation 37 can be obtained. Finally, equation 34, representing the front mass MSF, can be obtained from the moment equilibrium at the rear wheel contact point, and equation 38, representing the rear mass MSR, can be obtained from the moment equilibrium at the front wheel contact point. Now, let's move to the second method to find out the front and rear unsprung masses. In order to calculate the load transfer to the suspension link by the force generated by the sprung mass, as explained above, the sprung masses supported by the front and rear wheels must be obtained respectively. Let's first calculate how much of the vehicle's total load is loaded between the front and rear wheels without gravitational acceleration g. The load acting on the front wheels in the total vehicle load can be obtained using equation 39, and the load acting on the rear wheels can be obtained using equation 40. The sum of the loads acting on the front and rear wheels must be m, as shown in equation 41. Next, let's look at the relationship between the total vehicle load and the sprung load. The total sprung load can be expressed as the sum of the sprung load acting on the front wheels and the sprung load acting on the rear wheels, as shown in equation 1. If the longitudinal distance from the center of gravity of the sprung mass to the front axle is LSF, and the longitudinal distance to the rear axle is LSR, the masses MSF and MSR that the front and rear wheels must support can be expressed as the second equations of equations 42 and 43. As shown in the third equation of equations 42 and 43, the sprung mass acting on the front and rear wheels can be expressed as the total mass acting on the corresponding wheel minus the unsprung mass acting on the corresponding wheel. Therefore, The sprung mass MSF acting on the front wheel is the total mass MF acting on the front wheel minus the front unsprung mass MUF, so it can be expressed as in equation 42, and the sprung mass MSR acting on the rear wheel is the total mass MR acting on the rear wheel minus the rear unsprung mass MUR, so it can be expressed as in equation 43. The lateral force FSF acting on the roll center of the front suspension can be expressed as in equation 44 by multiplying the sprung mass MSF acting on the front wheel by the lateral acceleration AY, and the lateral force FSR acting on the roll center of the rear suspension can be expressed as in equation 45 by multiplying the sprung mass MSR acting on the rear wheel by the lateral acceleration AY. Since the moment generated by the lateral force acting on the roll center must be equal to the reaction moment generated by the load transfer delta FZLF generated by the load FSF acting on the roll center in the front suspension can be expressed as in equation 46, and the load transfer delta FZL generated by the load FSR acting on the roll center in the rear suspension can be expressed as in equation 47. Now that we know all 6 types of load transfers for lateral acceleration when a vehicle is driving at a constant speed with a constant turning radius, let's find equations to calculate the total load transfer that combines all of them for the front and rear wheels respectively. The load transfer generated by the unsprung mass of the front suspension can be expressed by equation 11, and the load transfer generated by the unsprung mass of the rear suspension can be expressed by equation 12. The load transfer of the front wheel, which is caused by the moment of the lateral acceleration acting on the sprung mass about the roll center, can be obtained by equation 29, and the load transfer generated by the rear wheel by equation 30. The load transfer of the front wheel, which is caused by the lateral force acting on the roll center due to the lateral acceleration of the sprung mass, can be calculated by equation 46, and the load transfer generated by the lateral force about the rear suspension roll center can be calculated by equation 47, respectively. The total load transfer at the front wheel is the sum of the load transfer due to the moment generated by the sprung mass, the load transfer due to the lateral force acting on the front suspension roll center, and the load transfer generated by the unsprung mass on the front axle, and can be expressed as in equation 48. The total load transfer at the rear wheel can be expressed in the same way as in equation 49. By substituting the load transfer calculation results of equations 11, 29, and 46 into equation 48, the total load transfer for the front wheel can be obtained as in equation 50, and by substituting equations 12, 30, and 47 into equation 49, the total load transfer for the rear wheel can be calculated as in equation 51. Let's learn about the load transfer moment distribution factor and the load transfer gradient. The front wheel load transfer moment distribution factor, as shown in equation 52, represents the ratio of the front wheel load transfer moment to the total load transfer moment, and the rear wheel load transfer moment distribution factor, as shown in equation 53, represents the ratio of the rear wheel load transfer moment to the total load transfer moment. When these front and rear wheel load transfer moment distribution factors are added together, it becomes 1, as shown in equation 54. The front or rear wheel load transfer moment factor represents the ratio at which the total load transfer amount is distributed to the front or rear wheels. The front wheel load transfer gradient is the change in front wheel vertical force with respect to the lateral acceleration. Therefore, it is the derivative of front wheel vertical force FZF with respect to lateral acceleration AY, as shown in equation 55, and the rear wheel load gradient is the change in rear wheel vertical force with respect to the lateral acceleration. Therefore, it is the derivative of rear wheel vertical force Fz with respect to lateral acceleration AY as shown in equation 56. Let's see how to calculate the lateral load transfer and weight distribution. Find the roll centers of the front and rear suspension. Calculate the roll moment of the sprung mass in terms of the roll angle at the front and rear suspensions. Find the roll angle using the overall roll couple curve or roll stiffness curve. Calculate the roll load transfer at the front and rear suspensions using the roll couple curve or roll stiffness curve. Calculate the front and rear lateral force acting on the roll center from the sprung mass. Calculate the sprung mass load transfer at the front and rear suspensions using the roll center height. Calculate the unsprung mass load transfer at the front and rear suspensions using the front and rear unsprung mass heights. Add together the roll stiffness moments due to the sprung mass at the front and rear suspensions, the load transfer through the suspension links, and the load transfer due to the unsprung masses. You can find this process on the page 268 of Dixon's book Tires, Suspensions, and Handling. Let's find out the answer to the quiz. Which of the following is related to the load transfer distribution that occurs between the front and rear wheels in a roll motion? Number 1. The unsprung mass is not related to the load transfer distribution. Number 2. The sprung mass is related to the load transfer distribution. Number 3. The lateral force acting on the roll center does not cause the sprung mass to roll, so it is not related to the load transfer distribution in roll motion. Number 4. The unsprung mass is not related, but the sprung mass is related. Therefore, the answer is number 2, sprung mass. Let's summarize the contents of this video. I explained how to calculate the 6 lateral load transfer elements caused by lateral acceleration. When the concept of the roll center is introduced to analyze the lateral load transfer, the force generated by the lateral acceleration at the center of gravity of the sprung mass is divided into the force transmitted to the spring and anti-roll bar in the form of a moment, and the force acting laterally on the roll center and transmitted to the suspension link. The moment transmitted to the spring and anti-roll bar can be further divided into the front suspension moment generated by the total sprung mass based on the vehicle roll center and the rear suspension moment generated by the total sprung mass based on the vehicle roll center. On the other hand, the lateral force transmitted to the suspension link can be divided into the lateral force acting on the front suspension roll center by the front sprung mass supported by the front suspension and the lateral force acting on the rear suspension roll center by the rear sprung mass supported by the rear suspension. Since the unsprung mass is not related to the roll center, no moment is generated about the roll center. The force generated by the unsprung mass can be divided into the lateral force acting on the front suspension unsprung mass center of gravity and the lateral force acting on the rear suspension unsprung mass center of gravity. In order to derive the formula simply, the following 5 assumptions are made. First, the sprung mass is assumed to be rigid. Therefore, no torsion of the sprung body is assumed. Second, the roll angle of the sprung body is assumed to be small. Therefore, the cosine of the roll angle pi is 1, and the sine of the roll angle pi can be used as the roll angle pi in radians. Third, the roll axis tilt angle alpha is assumed to be small. Therefore, the cosine alpha of the roll axis tilt angle alpha become 1. Fourth, the longitudinal axis passing through the roll axis and the center of gravity is assumed to be in the same vertical plane that runs through the center of the vehicle. Finally, the tire deformation is ignored. However, here, if the suspension stiffness is too large compared to the tire stiffness, the suspension displacement becomes relatively small and the tire deformation becomes relatively large, so the tire deformation should not be ignored. In this case, the tire deformation should be considered. Process to calculate the lateral load transfer and weight distribution can be summarized as follows. Find the roll centers of the front and rear suspension. Calculate the roll moment of the sprung mass in terms of the roll angle at the front and rear of the vehicle. Find the roll angle using the overall roll couple curve or roll stiffness curve. Calculate the roll load transfer at the front and rear using the roll couple curve or roll stiffness curve. Calculate the front and rear lateral force acting on the roll center from the sprung mass. Calculate the sprung mass load transfer at the front and rear using the roll center height. Calculate the unsprung mass load transfer at the front and rear using the unsprung mass height. Add together the roll stiffness moments due to the sprung mass at the front and rear, the load transfer through the suspension links, and the load transfer due to the unsprung mass. If you watch the previous videos, you can learn about various fields of automotive knowledge and enjoy a more in-depth understanding of future videos. In the last video, E0073, the fifth part of vehicle roll center, lateral load transfer considering roll center and tire lateral stiffness has been explained. Also, the principle of each momentum has been explained and a brief overview of the gyroscope precession effect that occurs in the vehicle rotating components and affects the lateral load transfer has been explained. In the latest video, H0073, the sixth part of vehicle roll center, we have looked in detail at how the gyroscopic effect of rotating vehicle parts affects handling. We have also looked at torque steer due to the gyroscopic effect during bumps and rebounds, and how the rotation of engine parts and vehicle wheels affects handling when the vehicle turns. The following video will be roll center part 8. I will explain how the load transfer distribution generated by the sprung mass during driving affects handling. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you at next videos. Goodbye guys.